A blessed day to everyone. Welcome to our class in GA Physics 101, Physics for Allied Health Professionals. And today we're going to have a post-laboratory discussion on experiment number 1, kinematics, experiment number 2, loss of motion, and experiment number 3, conservation of energy. Experiment number 1 again is about kinematics, and we have two parts for this experiment. The first part is to verify that the value of acceleration due to gravity is equal to 9.8 meters per second squared. And the second is to predict the horizontal and vertical distance of a ball shot at an angle. In this experiment, we have two parts. The first part is free-fall motion, and the second part is projectile motion. For the first part of this experiment, so we have this setup. We can see here the picket fence. We also have the Photogate head, and to connect the Photogate head to the Explorer GLX, we need to use a Photogate head cable, which is attached to the digital adapter, and then the digital adapter is connected to the Explorer GLX. And then to make the setup in place, we need a metal rod and also an A-base. So what we need to do here is just to drop the picket fence in the Photogate head, and the Photogate head will measure the position, which is the vertical displacement, and also the velocity of the picket fence. And then the position and also the velocity will be recorded in the Explorer GLX. Assuming that we have this reading after performing the experiment for the trial one, assuming that the reading on the Explorer GLX, we have the position which is equal to 0.3, and then for the velocity that is equal to 2.42. So these are the data that we're going to use to compute for the acceleration due to gravity. So we can see here the table for part 1. So the first column is about the trial. The second is for the vertical displacement, in which this is the position which is read on the Explorer GLX. Velocity, which is the third column, and the last column is for the acceleration due to gravity. And then we can also see here that we're going to have 5 trials, 1, 2, 3, 4, and 5 trials. The theoretical value for acceleration due to gravity is already given here, and that is equal to 9.8 meters per second squared. So what we need to do is we just have to record the position under the vertical displacement, and that is expressed in meters, and then for the velocity, which is the second reading, and that should be recorded here under the velocity. So these are actually the data for trial 1. So after trial 1, we need to perform again the experiment, and we need to get the data for trial 2, 3, 4, and 5. So assuming we have this data for the vertical displacement again, so that is 0.3, for the velocity that is 2.42 meters per second, and for acceleration due to gravity, we can compute the acceleration due to gravity using this formula. Acceleration due to gravity, which is g, is equal to v squared divided by 2y. The v here is the velocity, which is in the third column, and then the y is actually the value of the vertical displacement. After getting all the acceleration due to gravity for trial 1, trial 2, trial 3, 4, and 5, we need to get the average. So to compute for the average experimental acceleration due to gravity, we just have to add the 5 values and then divide it by 5, and we can get the experimental acceleration due to gravity, and that is the average value. Again, suppose we have 0.3, which is the value for the vertical displacement, and then for the velocity that is equal to 2.42. Let us compute now for acceleration due to gravity. Again, the formula for acceleration due to gravity is v squared divided by 2y. So based on the given, the velocity is equal to 2.42 meters per second. So we have to square this and then divide this by 2 multiplied by the vertical displacement or the position, which is equal to 0.3 meters. Okay, so using our calculator, so that will be equal to 2.42 squared, and then divided by 2 times 0.3, which is 0.6, and then the value here is 9.76. So the value of acceleration due to gravity here is 9.76 based on the given vertical displacement of 0.3 and velocity, which is 2.42. Assuming that the average value, assuming that the average value here after computing for the acceleration due to gravity for trial 2, 3, and 4, and 5, assuming that we computed for 9.82, assuming that this is the average value. So we need to compute for the percentage error. To compute for the percentage error, so the formula is experimental value, which is this one, okay, minus the theoretical value, which is 9.8 meters per second squared. So this is absolute value. So meaning if you get negative value, you just have to make that positive. So this is divided by the true value multiplied by 100. So since the given is 9.82 and 9.8, so let us compute now for the percentage error. So this is simply equal to 9.82 minus 9.80 absolute value over 9.80 multiplied by 100. So the value is equal to, again, 9.82 minus 9.80 and then divide by 9.80 multiplied by 100. So the percentage error here is equal to 0.20. So this one is equal to 0.20%. Okay, so this is the percentage error. So this is the first part of the experiment. Now let us proceed with the second part of the experiment, which is the projectile motion. So for the projectile motion, so we have here the projectile launcher, the photogate cable, which is used to connect the two photogate heads to the Explorer GLX. And we also use here the photogate head mounting bracket. This one is called the photogate head mounting bracket. And we have here the ramrod which is used to insert the ball inside the projectile launcher. And we have also to connect the time-of-flight accessory in the Explorer GLX to make sure the time of flight of the plastic ball. So the projectile launcher can be set to different ranges. Okay, we can set this to short range, to mid range, or to long range. But in our experiment, we only need to set the plastic ball in the short range, and we also need to set the angle of the elevation or the projectile in a certain angle, and then the angle depends on the data that we're going to assign to you by your professor or depending on your choice. And also we need here a table clamp, so that's to make the setup in place. So we need to launch the projectile here. Okay, we need to launch the plastic ball, okay, by just pulling the string here, and from that what will happen is that the plastic ball should touch the time of flight accessory. So once the plastic ball touch or land on the time of flight accessory, the Explorer GLX will record the initial velocity of the plastic ball and also the time of flight of the plastic ball. So from this data, so we make sure that the initial velocity is 3.08 meters per second, and the time for the plastic ball to land on the time of flight accessory is 0.7840 seconds. So again, in this experiment, we're going to predict the horizontal and vertical displacement of the plastic ball, okay, given a certain angle. So we need to put the initial velocity on the column for the TGLX, or for the VGLX, I mean, so that is expressed in meters per second. And then for the time of flight, so we have to place that on the second column, which is the TGLX for the time of flight. So again, so this is expressed in seconds, and then for the initial velocity, which is the VGLX, that is expressed in meters per second. After getting all the data here, okay, after getting the time of flight and also the initial velocity of the plastic ball, we need to compute for the vertical displacement and also the horizontal displacement. To compute for the vertical displacement, so we have to use this formula, y, which is the calculated value of the vertical displacement, that is equal to the initial velocity, which is the VGLX, sine theta. So whatever be the angle that you set on the Explorer GLX, so that's the angle here, and then the time here is actually the TGLX, okay, minus 1/2 multiplied by g, which is constant acceleration due to gravity. So in this one, we're going to use 9.8 meters per second squared, and then the square of the time GLX. So this is how to compute for the y calculated. And then for the x calculated, we're going to use this formula, x, which is the horizontal displacement, that is equal to the initial velocity. Again, this is equal to the BGLX, which is the reading here, and then the cosine theta, and then multiplied by the time, which is also the TGLX. So the TGLX again is on the second column. So these are the formulas that we are going to use to compute for the y calculated and also the x calculated. Now the question is, how can we get the y measured and also the x measured? The y measured can be measured, okay, it can be measured using steel tape. So we have to measure the height of the plastic ball from the tip or from the mouth of the projectile launcher. So using steel tape, so we can measure the y. So that's the y measured. And then so since this is the, for example, this is the time of flight accessory, and then the ball will land here. Okay, so we need to measure the x horizontal displacement from this point. Okay, so from this point to that point, so that's actually the value of the x measured. So we now have the y measured, the y calculated, the x measured, and the x calculated. So we need to perform this experiment in 5 times or 5 trials. And then after that, again, so we have to compute for all the y measured. We have to measure the y and also compute for the y calculated for all the trials. And then after that, we have to compute for the average. Again, to compute for the average, we just have to get the sum and then divided by 5. Okay, the same thing with this one, the summation divided by 5, the summation of the x measured divided by 5, same thing with the x calculated. So this is the summation of the x calculated divided by 5. And then after that, we have to compute for the percentage difference using the formula. So the percentage difference has different formula with the percentage error. So in this one, so we have to know the value 1. So the value 1 can be the y measured. It can be also the y calculated. Okay, minus value 2. Again, the value 2 can be the y measured or the y calculated. Again, this is absolute value. If you get negative value, you just have to make that positive. Okay, divided by the average, you need to get the average now 1 and 2. So value 1 plus value 2. Okay, and then it should be divided by 2. So this is the average multiplied by 100. So this is how to compute for the percentage difference. Okay, so in this experiment, so we have 2 questions. Okay, the first question is, you throw a ball up in the air so that it rises to a maximum height much greater than to the height of a 20-feet tree. Is the magnitude of the acceleration greater while it is being thrown upward or as it falls? We have to explain. Okay, the question here is, what is the value of the acceleration, or what is the acceleration here? So the first question is about the free fall motion, in which again, free fall motion, so this is the kind of motion in which this is influenced by the force of gravity. So the acceleration here is actually the acceleration due to gravity. And then we know that the acceleration due to gravity is constant. So this is equal to g, in which acceleration due to gravity is equal to 9.8 meters per second squared. So the magnitude of this acceleration is always 9.8 meters per second squared, regardless if the object is going up, going down. So the value is always 9.8 meters per second squared. So the answer here is, this is constant. They have equal value of the acceleration. And then again, that acceleration is equal to 9.8 meters per second squared. So question number 2 is about projectile motion. So we have 2 cases here. The first is a bullet. Okay, assuming this is the bullet that is shot horizontally, and then it undergo projectile motion. And then the second bullet is drop. Okay, so this is free fall motion. Okay, so they have the same height. Okay, they have the same height. So the question is if there's no air resistance, which bullet hits the ground first? We have to explain. So we can explain this by getting the formula to compute for time. Okay, so we need to compute for the time here. If the time for the first case is equal to the time for the second case, so meaning they will hit the ground at the same time. So we need to compute for the time. Again, so this one is about projectile motion. So since the bullet here is moving horizontally, so we can say that the BOX here is equal to the whatever be the given value of the initial. And then since the BOX is already here, and that is again, the bullet here is moving horizontally, so we can say that the BOY here is equal to 0. So again, so we have the value for y, and to compute for y, the formula is BO multiplied by sine theta multiplied by t minus 1/2 t squared. Again, the BO sine theta here is equal to the BOY. In our case here, in case letter A, the BOY is 0. So meaning we can cancel this, and then the formula will become negative 1/2 t squared. But again, so since the bullet is below the starting point, so we can say that the y here is negative also. So that's below the starting point. So here we need to derive the formula for time. So just derive the formula for time. So time here is equal to 2y divided by t. So this is the formula for time for the first case. On the second case, so again, so this is free fall motion. And then according to the problem, so you drop a bullet. So meaning initial velocity here is equal to 0. So the y here is also given. So for the free fall motion, to compute for the vertical displacement, so y is equal to initial velocity, BOT, minus 1/2 t squared. So this is the formula. Again, so the object here is below the starting point. We can set the y here as negative. So this will be 0 because the initial velocity is 0. So the formula now will become negative y is equal to negative 1/2 t squared. Again, the target is to compute for time. So time is equal to 2y divided by g. So what can we say about the formula? So the formula of the first case is the same with the formula for the second case. So they are equal. So the answer here is they will hit the ground at the same time. Okay, so this is experiment number 1. Okay, so let's now proceed with experiment number 2. And experiment number 2 is about laws of motion. We have 3 objectives here. The first objective is to determine the mass of an object in static equilibrium. Second, determine the moments of force in an equal arm balance. And third, study second law of motion. So let's start with the first objective, or the first part of the experiment, which is about translational equilibrium. For translational equilibrium, we have this setup. Okay, we have the dynamics card, which is placed in the dynamics track. We need to use angle indicator to measure the angle. And we have here actually a force sensor. So this is used to measure the tension on the string, which is connected to the dynamics card. And the force sensor is connected to the Explorer GLX to record the reading on the tension or on the force. We need a universal clamp here and also metal rod, okay, or stand. So here we're going to apply here the first condition for equilibrium. So when we say equilibrium, so this is the state of a body in which there's no change in the motion. So we can say that there's no change in the motion if the object is at rest. So in this case, the object is actually in the state of rest. So the first condition for equilibrium actually is summation of forces on x, it should be 0, and then the summation of our y is equal to 0. So this is actually the first condition for equilibrium. The first condition of equilibrium is actually the under the translational equilibrium. So the target here is to compute for the mass of the card, so which is equal to tension divided by g sine theta. So we need to identify all the forces acting on the card, and then based on that, we have here the normal force, which is the force perpendicular to the surface. Also here we have the weight of the card, and attached to the force sensors, of course, we have the string here. So there's a tension here. So we're going to draw this in a free body diagram. So the tension will be in this direction. And then we have to measure the angle also, the angle. And the normal force is perpendicular. So we have here the normal force and the weight of the card. So we're going to rotate this one. So that will become like this. Okay, the tension will be on this axis. the normal force will be on the y-axis, and then there will be rotation on the weight with a certain angle. So this is now the weight. So we're going to apply the summation of forces on x equal to 0. So we will arrive on this formula. But anyway, we need to use this formula, summation of forces on x equal to 0. So we have to identify all the forces acting on the cart on the x direction. So these are the tension which is going to the right, so that will be positive. And then for the y, we have w sub y and w sub x. So in this case, we're going to use w sub x. So w sub x is the horizontal component of the weight, or w. So to compute for w sub x, this is w multiplied by sine theta. So this is going to the left, meaning that will be negative. Minus w sine theta equal to, it should be equal to 0. Okay, to satisfy equilibrium, the sum should be equal to 0. So to compute for weight, weight is simply mg. So therefore, we can replace w by mg. So this will become tension minus mg sine theta equal to 0. And then from that, we can transpose mg sine theta on the other side. So this will become tension equal to mg sine theta. So the target is to compute for the mass of the cart, this variable or this quantity. So we just have to divide both sides by g sine theta. So the final formula is this one. So mass is equal to tension divided by g sine theta. So we're using force sensor here to measure the force or the tension. And then on the screen of the Explorer GLX, so we can see here the tension or the force. So the tension here is expressed in Newton. So meaning if the reading is 1.32, so this is 1.32 newtons. And then this is again the tension or the force which is read by the force sensor. We just have to place the reading on the force sensor or the value of the tension on this part, okay, on the column for the tension. And then we can see here on the second column, we have the angle which is 15 degrees and 20 degrees. So meaning we need to incline or to change the angle of the dynamics track from 15 to 20. So we need to start at 15 degrees. So at 15 degrees angle, so the reading for the tension is 1.32. Again, so we need to compare the mass of the cart, experimental and also theoretical. For the experimental value, okay, we're going to use this formula. Okay, so that's equal to tension divided by g sine theta. And then for the theoretical value, we need to measure the mass of the cart using top loading balance. We just have to place the dynamics cart in the top loading balance, and then whatever be the reading there, so that is the reading for the mass of the dynamics cart. And then please take note, guys, that if we're going to use the top loading balance, the reading is in grams. So we need to convert this to kilograms. And then whatever be the reading there, we just have to place that here. So that will be the theoretical value. Again, the theoretical value is the measured value of the mass from the top loading balance. And then experimental value, we have to use the formula T over g sine theta. And after that, we have to compute for the percentage error after computing for the experimental and also after getting the theoretical value. Percent error is the theoretical mass minus the experimental mass over theoretical mass multiplied by 100. So let us compute this one. Again, the tension here is 1.32. Okay, again, the formula for the experimental value, okay, mass is T over g sine theta. So the tension here is 1.32 newtons over g, which is constant. This is 9.8 meters per second squared. Okay, multiplied by sine. So the angle here is 15 degrees. So this is sine 15 degrees. Okay, so the value here is equal to. Okay, so let's compute this one. So this is 1.32. Okay, divided by 9.8 multiplied by sine 15. So the answer here is 0.52. So this one is 0.52 kilograms. So we have to place the 0.52 kilograms. Again, this is the experimental value. We have to place that here. So assuming that the theoretical value, or after measuring the cart using top loading balance, is, let's say this is let's say this is equal to 517.65 grams. So we just have to convert this one into kilograms. So divide this by 1000 and then round off this one into 2 decimal places. So this will be 0.52 kilograms. So this is the volume. Okay, so since this is 0.52, this is also 0.52. So percentage error should be automatic to be 0%. Again, the formula is 0.52 minus 0.52 over the theoretical value, which is also 0.52 times 100 absolute value. Again, this is equal to 0. So this is the percentage errors, and then this is the first part of the experiment number 2. Okay, for the second part, the objective is to determine the moments of force in an equal arm balance. So we have this set up. We need equal arm balance, and then in the equal arm balance, we can see here that we have loop 1, okay, loop 2, loop 3, and then also on the other side, loop 1, loop 2, and loop 3. And here, this part is actually for the first column of our experiment, and then this is for the second column of the experiment. So this is for the hanging mass, and the other side is actually for the applied force. So for the hanging mass, we need to use, of course, different masses here. And for the applied force, so whatever be the reading here, using the force sensor, so that's the value of the applied force. And then since we're talking about the hanging mass here, so therefore we need to get the F1 here. And then the F1 here is actually equal to the weight of the hanging mass. So to compute for that, that is simply mass of that object, of the hanging mass, multiplied by acceleration due to gravity. And then the acceleration due to gravity here is, we're going to use 980 centimeters per second squared, because the mass here is expressed in grams. And then for the force sensor, so the reading here will be in newtons. So therefore we need to convert newtons into dynes, and that can be converted by just multiplying this one by 100,000 to make that dyne. Okay, so what we need to do here is to balance the equal arm, and on the left side we need to place here an hanging mass, and then on the second, on the other side, we need to place there a force sensor. And also we need also to compute for the R and also the angle. For loop 1, for loop 2, and for loop 3, there are different values for R and also different values of the theta. For R, okay, so this is the formula, this is Pythagorean theorem. So to compute for the lever arm, okay, or the distance from the applied force to the point of rotation, so that's equal to the square root of x squared plus y squared. Okay, the x here is actually the distance, this one. Okay, assuming we have, if this is the loop 1, so x, and then this is the y, this is the value of y. So you have the x, you have the y, you can compute here the r. And then again, this is a right triangle, meaning we can use the Pythagorean theorem. And then for the angle we can use tangent theta. Okay, so angle is equal to tangent or arctangent y over x. And then for the torque, so this one we need to compute the torque on the left side and also the torque on the right side. And then our target is this should be equal. So the torque on the right side should be equal to the torque on the other side, to make the system in equilibrium or rotational equilibrium. So the formula to compute for torque is this one. So we have force, applied force, or the weight of the hanging mass, multiplied by the lever R, and then multiplied by the cosine of the angle. So we can see here the table showing the value of R and also the value of theta given the different loops. Okay, for loop number 1, the value of R is 8.06 and the angle is 45 degrees. So where is loop number 1? Loop number 1 is here. Okay, so the length of this is equal to 8.06 centimeters, and then the angle here is 45 degrees. For the second loop, okay, the value of the R is 12.75 and then the angle is 26.57. For the third loop, 8.02 centimeters as the value of R, and then for the theta, that's 18.43 degrees. So we need to identify the position of the hanging mass and also the position of the applied force. So wherever be the position, okay, whatever be the position of the hanging mass and also the applied force, so we need to identify the loop number, and then whatever be that loop number, we just have to copy the value of r and theta based on the given loop number. So this is actually the setup again. This left side is intended for the first table, which is the hanging mass, and then the second part, or the second side, or the left side or the right side, this is intended for the applied force. Again, so the hanging mass should be placed here. Okay, assuming this is 50 grams, so the 50 grams should be placed here. And then as we can see, this is 0, loop number 1, loop number 2, so the hanging mass is placed at loop number 2. Okay, and then for the right side, so the force sensor is placed at loop number 2, so that's why this is loop number 2. And then whatever be the reading here, we just have to place that here for the value of the applied force. Again, the value of F1, we just have to multiply 50 by 980 centimeters per second squared. Okay, we can get the F1. And then R1 and theta 1, so they are the values of the lever arm and also the angle, okay, on loop number 2. So we need to look at the table showing the value of R and also the value of theta. And then torque 1, again, the formula for torque, that is F R cosine theta. And then for the applied force, again, we need to copy the reading here and then multiply this by 100,000 to get the value of F2. Again, so this is also on loop number 2. So what is the value of R and theta on loop number 2? And then compute for the torque on the right side. Again, so we have to place the hanging mass 50 on this side. Again, this is placed on loop number 2. And then the reading here should be placed here at the applied force. And then again, this is also at loop number 2. Okay, example. Okay, assuming that the reading on the force sensor, okay, on the right side of the equal arm balance is 0.50. Okay, assuming that is the value. So let's now solve the value of the torque on the right side and the torque on the left side. Okay, anyway, so we have this formulas. Okay, we have different values for loop, and loop number will be provided anyway, so that can be seen on the table. So the value of R and also the value of theta depending on the loop number. And again, the value of F1 here, we should multiply this by 980 centimeters per second squared. And then for the F2, you need to multiply this by 100,000 to convert the Newton into dyne. And compute for the torque 1 and also torque 2, the formula is R multiplied by F cosine theta. And whatever be the reading for the first data, or for the first table, you just have to copy that on the third column and on the third table, and also the data on the torque from the second table, you just have to copy that to the third table. And then after that, you have to compute for the percentage error. Guys, please take note that in this one, the theoretical value here is the table 1, okay, torque 1. The torque 1 is considered as the theoretical value. So that's why we are computing for the percentage error. Again, the formula is torque 1 minus torque 2, absolute value divided by torque 1, which is the absolute, or which is the theoretical value, multiplied by 100. Okay, so let's try to compute this one. Okay, the given here is, okay, so mass is 50 grams. Again, we need to multiply the 50 by 980. So this is 50 multiplied by 980. So the answer here is 49,000. Okay, this is 49,000 times. And then the 50 grams is at loop number 2. So what is the value of R and theta at loop number 2? So this is 12.75. And then theta is 26.57. Now let us compute for the torque. So the formula is F1 R multiplied by cosine theta. So this is 49,000. Again, so let me write here the formula. So this is the formula, FR cosine theta. Okay, so F is 49,000 multiplied by 12.75, and then multiplied by cosine 26.57. So the answer here is 558,769 0.25. So let me round up this one into the decimal places. Okay, so this is for the first column or your first table. Okay, for the first table. On the second table, so the applied force is also equal to 0.50. Again, we need to multiply this by 100,000. So the value here is 0.50 multiplied by 100,000. So this is equal to 50,000. And then again, so this is at loop number 2. This is also 12.75 and 26.57. So let's compute for the torque. So 50,000, okay, multiplied by 12.75 and then multiplied by cosine 26.57. So the answer here is 570172, okay, 0.71. So this is the torque on the right side. Now I'm going just need to copy on the third table. This is 578769.25, and then the torque 2 is 570,172.71. Now let's compute for the percentage error. Okay, so this is equal to 558769.25 minus 570172.71, okay, divided by the theoretical value, which is torque 1, 558769.25, and then multiply this by 100. So the answer is 2.04. So the percentage error here is 2.04%. Okay. So this is the second part of the experiment. Now let's move to the third part of experiment number 2, which is to study second law of motion. Anyway, so second law of motion is the law of acceleration, in which under the second law of acceleration, or the second law of motion, which is the law of acceleration, so we are following this formula. So summation of force is equal to mass multiplied by acceleration. So we can see that the mass is directly proportional to the force. Acceleration is also directly proportional to the force, but acceleration is inversely proportional to the mass of the given object. So this one, so we have two objects here. The first one is the hanging mass, and the second is the dynamics cart. So they are connected by a string, and then what we're going to do here is we just set a certain distance here to the end point, okay, to this block or to this stopper, okay, from this plunger to the stopper. So this is actually the distance, or x. So we need to use a stopwatch to measure the time. Okay, so from this point to that point, we need to get or to release the cart. And then what will happen is, if we're going to release the cart here, the hanging mass will be also accelerating downward. So we can get the time here, and then the distance is given. So we can actually compute the acceleration here. So based on the formula for the per motion, so acceleration here is equal to 2 multiplied by x divided by t squared. Okay, this is the experimental value of the acceleration of the cart. Now, how can we compute for the theoretical value, or for the accepted value of the acceleration of the cart? So we need to treat these two objects separately, and then we need to identify all the forces acting here. Of course, again, so we have the weight of the cart, we have the normal force, in which the weight of the cart is equal to the normal force, so they will be cancelled. And this is attached to the string, so we have here the tension. So on the cart, okay, at cart, so summation of forces is equal to ma. So the force here is tension equal to, so this is the mass of the cart. Okay, let me use mc as mass of the cart multiplied by the acceleration. So this is the formula for the cart. Okay, for the hanging mass, so what are the forces? We have the weight of the hanging mass, and we also have the tension here. And then we also need to use this formula, summation of forces equal to ma. So tension is going upward, this is positive. Weight is going downward, so this is negative. And then this is equal to hanging mass. Let me use mh for the hanging mass. Okay, multiplied by acceleration. So the tension here actually is the same. So the tension from the cart is also the tension on the hanging mass. So they are equal because they are attached by one string. Okay, they are attached by one string. So we can say that whatever be the velocity of the cart, that is also the velocity of the hanging mass. And therefore, whatever be the acceleration of the cart, that is also the acceleration of the hanging mass. So meaning acceleration here and the tension on the first formula here is also the tension and also the acceleration on the second formula for the hanging mass. So what we're going to do is we just have to substitute, okay, the first equation to the second equation. So that will become, so tension is equal to MCA. So I'll be replacing tension by the first formula or the first equation. So that's MCA, okay, and then minus weight. Okay, so this is the weight of the hanging mass. So this is mass of hanging, or hanging mass multiplied by G. Okay, hanging mass multiplied by G. Okay, equal to, okay, again, so this is accelerating downward. So the acceleration here should be negative. So we have here negative acceleration. So minus hanging mass multiplied by acceleration. Okay, so what we're going to do is we just have to put like terms on one side. So that will be mass of the cart, acceleration, plus hanging mass multiplied by acceleration. Transpose this on the other side, hanging mass multiplied by G. So acceleration is equal to, okay, anyway, let's just factor this one, mc plus mh, okay, equal to mh multiplied by G. So this is G, okay, G. Okay, the target is to compute for acceleration. Okay, so acceleration, okay, divide both sides by mc plus mh. So acceleration here is equal to hanging mass multiplied by G over mc plus mh. Okay, mc plus mh is actually the total mass. So this is the formula for the theoretical value of the acceleration of the cart. Okay, again, so we have this set up. The formula for the experimental value is 2x over t squared. Again, the x is the distance and the time that can be measured using a stopwatch. And hanging mass, okay, this is the value of the hanging mass. Whatever be the mass of this one, that is the value here, multiplied by acceleration due to gravity, which is, in this case, we're going to use 9.8 meters per second squared. Okay, meaning in this one, we need to convert this to, or we can use actually 980 centimeters per second squared. So because the given here is in grams. But if this one is expressed in kilograms, so meaning we need to use the 9.8 meters per second squared. Okay, so let me erase this one. Okay, so divided by the mass total, so that will be the mass of the cart plus the hanging mass. So this is the mass total, mass of cart plus the hanging mass. Okay, so this is the table. We can see here the mass of the dynamics cart. So we can compute or measure the mass of the dynamic cart here using top loading balance. Okay, this is expressed in grams. And then the distance depends on your choice. You can set the distance by group. And here is the hanging mass. Okay, it can be 20 grams or 50 grams. And the mass total, again, to compute for the mass total, we simply add the mass of the dynamics cart and the hanging mass. Okay, so we can get the mass total. And then we need to perform the experiment 3 times. Okay, first trial, second trial, the third trial. Okay, we need to measure the time, and then after that, get the sum divided by 3, and then we can compute the average time. And let's compute for experimental value of acceleration. Again, the formula is 2 multiplied by the distance. Okay, whatever be the value here, multiplied by 2 divided by the square of the average time, so we can compute the experimental value of the acceleration. And then for the theoretical, okay, that will be 20 grams or the hanging mass multiplied by 980 centimeters per second squared divided by the m total, or that is the sum of the hanging mass and also the mass of the cart. Okay, so we can compute the theoretical value. And then for certain error, again, theoretical value minus experimental value over the theoretical acceleration multiplied by 100. Okay, again, so we have the these are the formulas, or these are the guide. And suppose we have these values. Okay, after measuring the cart using top loading balance, so we measured that the cart has a mass of 517.65 grams. And then we set the distance at 60 centimeters. Okay, so after doing the 3 trials, we came up that the values for the time are 1.79, 1.80, and 1.82. Okay, we need to get the average. Okay, so let me start computing for the experimental value. So to compute for the experimental value, again, the formula is 2x over t squared. Okay, so we need to compute for the average. That's 1.79 plus 1.80 plus 1.82. Okay, divide this by 3. So the answer here is 1.80. So let's use two decimal places. 1.80. Okay, this is the time, the average time. So we have the given distance here. Now we can compute the value of experimental value of acceleration. So acceleration is 2x over t squared. Okay, this is 2 multiplied by 60 centimeters. Okay, over 1.80 second square. Okay, this is equal to. So the value of the acceleration here is 37.04. This is 37.04 centimeters per second squared. So this is the experimental value, centimeters per second squared. Okay, now let's compute for the theoretical value. Again, the formula is this one. Okay, so we have acceleration is equal to, so the given mass here, the hanging mass is 20 grams. So 20 grams multiplied by 980 centimeters per second squared, and then divide this by the mass total. So what is the mass total? 20 grams plus 517.65. So this is 537.65. This is the total. Okay, again, 20 grams plus 517.65. This is 537. So over 537.65. Okay, this is equal to 20 times 980 divided by 537.65. So the answer here is 36.45. So this one is equal to 36.45. So I'm going to write here the value of the theoretical value, 36.45. Then after that, let's compute for the percentage error. Okay, so we have 37.04 minus 36.45, and then divided by the theoretical value, 36.45, multiplied by 100. So this is equal to 1.618 or 1.62. So the percentage error here is 1.62. Okay, so this is the last part of experiment number 2. Okay, so let us proceed with the, anyway, so we have 3 questions here, okay, under experiment number 2. Okay, the first question is, how close was your calculated mass to the actual mass? Okay, so you can actually answer here by computing the, you have to compare the calculated mass. Okay, the calculated mass can be computed by this formula. Okay, and then the actual mass, this is using top loading balance. And then to answer this, how close? Okay, you can actually answer this one by computing the percentage error. If the percentage error is 0, so meaning they are equal. So the actual mass is equal to the calculated mass. And then if this is, the percentage error is big, okay, so meaning they are not equal. So meaning you can answer number 1 by just looking at the value of the calculated mass and also the value of the actual mass. And also based on the percentage error, you can actually determine how close is the calculated with the actual mass to the actual mass. And number 2, if the 2 children of unequal weights are playing in a seesaw, what are the possible ways in which they can balance the seesaw? Okay, if we have 2 unequal weights, okay, assuming that person 1, okay, or weight 1 is equal to, okay, let's just assume that this is okay, this is 4 kilograms. Okay, that's very small, okay, or let's make it more realistic. Okay, let's make it 44 kilograms. This is weight 1. And then weight 2, let's say this is bigger, okay, or heavier, 88 kilograms. So meaning we can say that weight 2 is twice of W1. Okay, if they will be sitting on a seesaw, okay, assuming this is the seesaw, okay, this is the center, okay, the weight 1 should be, okay, and then assuming that the distance here, okay, assuming that the length of the seesaw is, let's say this is 4 meters. Okay, this is 4 meters, so meaning this is 2 meters, and then this is also 2 meters. So to balance the seesaw, the person 1 should be sitting, okay, we can actually, okay, ask the person one to sit here, okay, to sit here and weight 1, and then the 88 kilograms child, okay, should be sitting somewhere here, okay. So we can set this one at maybe at 1 meter, okay. So the weight 1 should be sitting here, okay. So meaning, guys, the heavier child should be sitting close to the fulcrum, and then the lighter person should be sitting on the farther from the fulcrum, okay. So to balance the seesaw, again, it depends on their weight. It depends on their weight. Okay, question number 3. What's the relationship of the hanging mass to the acceleration of the cart to time of travel? Okay, so we're going to relate hanging mass to acceleration of the cart. Okay, again, acceleration is equal to, based on the theoretical value, hanging mass over m total. This is the formula. Okay, so we have the hanging mass, acceleration, so they are directly proportional. So if there will be increase in the hanging mass, there will be also increase in the acceleration. So they are directly proportional. Okay, how about hanging mass to time of travel? Okay, we can also compute acceleration using the first formula, 2x over t squared. Again, so this is the hanging mass, and then we have here the time. So they are what? They are inversely proportional. So the heavier will be the mass. Okay, the heavier will be the mass, the shorter will be the time. Okay, so they are inversely proportional. So these are the answers for experiment number 2. Now let us proceed with the last experiment. Okay, last experiment is about conservation of energy. Okay, and then we have two objectives. The first is to verify the law of conservation of energy, and then the second is to determine the relationship between the change in the gravitational potential energy and the kinetic energy of the falling object. So again, in principle, okay, the change in gravitational potential energy is equal to the change in the kinetic energy. So they are equal. So the law of conservation of energy, so meaning we need to get the total energy, and then the total energy in the system should be conserved. It should be the same. So to compute for the total energy, so this is kinetic energy plus gravitational potential energy. So meaning at any point here, after computing the KE and also the GPE, and then compute the total, so the total energy at any point here should be conserved. So it should be equal. So the sum of the GP and the kinetic energy should be always the value of the total energy here. So it should be constant. Okay, so we have the setup. We have the motion sensor and the metal rod, a base, Explorer GLX. So the motion sensor is used to measure the position or vertical displacement, and also to measure the velocity. So we're going to use the position in computing for the gravitational potential energy, and the velocity will be used to compute for the kinetic energy. Okay. Again, gravitational potential energy is mgy, so the mass of the ball, acceleration due to gravity, which is constant, that is 9.8 meters per second squared, and then the position or the vertical displacement. And then for the velocity, we're going to use that to compute for the kinetic energy. So the formula is 1/2 mv squared. Again, this is the mass of the ball, and then the square of the velocity. Okay, assuming after performing the first trial, so we have this data. Okay, on the GLX, we see here that the position is, we have this values 0.447, which is the corresponding value of the velocity, which is 2.93. But in this case, I'll be using these values. Okay, I'll be using these values. So the position is 0.747 and the velocity is 3.82. So what I'm going to do is I'm going to compute for the gravitational potential energy and also the value for the kinetic energy. And then I'll be comparing the two. And then the target is they should have the same value, because the gravitational potential energy is converted to the kinetic energy. So the total energy should be conserved. Okay, again, so we need to compute for the percentage difference, and then this is the formula. And then the kinetic energy, we have 1/2 mv squared. Gravitational potential energy is mgy. and then the data was shown to you. Okay, that is the which is displayed in the Explorer GLX. Okay, assuming we have these values. Okay, after measuring the mass of the ball using top loading balance, the value is 0.0097 kilograms, or this is 9.7 grams. We need to convert this to kilograms, and then the readings are, the position is 0.747 and then the velocity is 3.82. Now let's compute now for the gravitational potential energy. So that's based on the position. Again, the formula is mgy. So this is 0.0097. This is the volume of the mass multiplied by 9.8, which is acceleration due to gravity, and then multiplied by the height, 0.747. Okay, so the answer here is, so let me use part decimal places, 0.070. Okay, so this is joule. Okay, this is the value of the gravitational potential energy. Now again, this is the volume. Okay, this is mgy. Okay, mass is 0.0097 kilograms, and then multiplied by 9.8 meters per second squared, and then to be multiplied by 0.747, okay, meters. Okay, this is equal to 0.0710, okay, joule. And then for the kinetic energy, the formula is 1/2 mv squared. This is 1/2 multiplied by the mass, 97 kilograms, and then v squared, so 3.82, okay, meters per second square. Okay, so what's the value here? Okay, so this one is, again, 1/2 multiplied by 0.0097, okay, then multiplied by 3.82 square. So the value here is 0.070. Again, let's use part decimal places, 8 joule. Okay, then after that, let's compute for the percentage error. Okay, so percentage difference. This is simply 0.070 or 710 minus 0.0708, okay, absolute value, over 0.0710 minus 0.0708 plus, this is plus, okay, divided by 2, okay, multiplied by 100. Okay, so this one is equal to 0.0710, okay, minus 0.0708, and then divide by the average, 0.0710 plus 0.0708, okay, then divided by 2, and then multiplied by 100. So the answer is 0.28. So this is the percentage difference, 0.28. Okay, so we have two questions here. Okay, what will happen to the potential and kinetic energy as the ball pulls? Okay, as the ball pulls, okay, so at the highest point, okay, at the highest point, gravitational potential energy is the maximum, at maximum value. Okay, and then what will happen is, as the ball pulls, okay, it will change its height. So therefore, there will be decrease in the value of the gravitational potential energy. Okay, there will be changes, or there will be decrease in the value of gravitational potential energy because there is decrease in the value of the height. Okay, again, we know that Gp is directly proportional to the height. Okay, so as we decrease the height, there will be also decrease in the gravitational potential energy. So what will happen to the value of the energy there? So the energy will be transformed into kinetic energy. So at this one, so initial velocity here is 0, so therefore the kinetic energy here is 0. So as the ball falls, there will be increase in the velocity, or in the speed of the ball. So meaning, if there will be increase in the velocity, there will be also increase in the kinetic energy. Again, the formula for kinetic energy is 1/2 mv squared. So velocity is directly proportional to the kinetic energy. So as the ball pulls, the gravitational potential energy decrease, and then the kinetic energy will increase. Okay, so again, the gravitational potential energy is converted to the kinetic energy. But again, total energy is equal to Ke plus Gpe. So the total should be the same. okay, in any height there. Okay, because again, so that is the principle of conservation of energy. What is the relationship between of kinetic energy and potential energy as the ball pulse? So what can you say about the relationship? So kinetic energy is directly proportional to the, or inversely proportional to the gravitational potential energy. Okay, so increase in the kinetic energy, there will be decrease in the gravitational potential energy, and vice versa. Okay, so that's the relationship. So they are inversely proportional.